Hello everyone, and welcome to this video on finding tangents to polar curves. And in this video we are going to specifically look at finding tangents parallel to the initial line. So if I have let's say I just have this polar curve, finding a tangent parallel to the initial line, but also perpendicular to the initial line. So hopefully you recall from P4 that we can, if we have an equation in parametric form, let's say I have x equal some function of t and I've got y equals some function of t, then I can differentiate them and I will have dx dt and I will have dy dt, and I can then by the chain rule use this to find dy by dx. Now, for polar curves, we are going to use the same principle in order to find parallel and perpendicular tangents. So I know that when my r is some function of theta, and I can state that the parametric equivalent, because we've looked at in previous videos, in the very first video, how to write x as a function of theta. We know that x is equal to r cos theta, and we also know that y is equal to r sine theta. If I use this idea and I look at equations parallel to the initial line, as I've stated up here, then at this point here I know that dy by d theta is equal to 0, because obviously this horizontal line is going to be in the form y equals some function, and my vertical line, so perpendicular down here, is going to be in the form x equal to some constant. And therefore when I have tangents perpendicular to my curve, I'm going to use the fact that I know that dx d theta must equal 0. Okay, so I've summarized this in a little diagram here, and that's essentially all we are going to do. We're going to solve these problems. Parallel to the initial line, dy by d theta equals 0, and perpendicular to the initial line, dx d theta equals 0. Okay. So let's start with the first example here. The question says find the coordinates of the points on that polar graph where the tangents are parallel to the initial line. So where dy d theta is equal to 0. And if I go back to this diagram here, there will obviously be two places where this occurs. This also happens down here. Dy by d theta is also going to equal down here. So they're asking me to find these coordinates at the tangent, where the tangent meets, where the line meets, is tangent to the curve. Okay, so I am obviously going to look for dy by d theta. And in order to get dy by d theta, I need to write this equation in terms of y. I know that y, let me use yellow, y is equal to r sine theta. And I'm told in the question that r is equal to a times 1 plus cos theta. So therefore, I get sine theta multiplied by a plus a cos theta. If I expand these brackets, a plus a cos theta. And so this ends up being a sine theta plus a sine theta cos theta. And now I'm ready to find dy by d theta. So I know I want the point where dy by d theta is equal to 0, and so therefore where a cos theta, so, and here I need to apply the product rule. So it's the first term sine theta times by the derivative of cos theta, which is negative sine theta, plus the derivative of the first term, which is going to be a cos theta times by the second term cos theta, and where that's equal to 0. So straight away here I also notice I can divide by a, the constant that we have, and I end up with cos theta minus sine squared theta plus cos squared theta is equal to 0. Okay, so I notice now that I have a trig equation. I'm going to rewrite everything in terms of cosine. So I'm going to replace this sine squared with 1 minus cos squared theta plus cos squared theta equals 0. And I'm going to therefore end up with 2 cos squared theta plus cos theta minus 1 equals 0. This can be factorized, so I get 2 cos theta and cos theta there, plus 1 minus 1. So 2 solutions for cos theta, a half, or cos theta equals -1. Okay, right, let's just make a little bit more space. Right, so if I sketch this, I'm going to get a cardioid that looks like this. Okay, not a great sketch, but that'll have to do. Okay, and my lines parallel to the initial line will be across there, and it will be across here, and it's actually also, there's actually also going to be a tangent here at this point. So I'm going to get a tangent there, and at this point, for my r and theta value there, I will also have a tangent, okay, at this exact point there if we zoom in. So I'm trying to work out here the angle there at which I have my point, the angle here, which will obviously be negative theta. And well, at this point now I know I've gone all the way from 0 to pi, okay, which also corresponds to where cosine is equal to -1. It is at pi. So I can then work out my solutions here, and I will see that I have theta equaling to plus minus pi by 3 and theta equaling to pi. And so that there is how I am going to work out sorry, I just need to replace that. And theta equaling to pi. And now that I have those values, I can find my r value. So I'm just subbing my values of theta into r equals a times 1 plus cos theta. And that in the case of plus minus pi by 3, when I sub that in both of those cases, I will have r equals 3/2. And in this case, I will have r is equal to 0. So those are the coordinates at which I am, where the tangents are parallel to the initial line. It will be at 3/2 and pi by 3. It will be at 3/2 and negative pi by 3, and it will be at 0 and pi. Okay, hope that made sense. Okay, example 2 says find the equations and the point of contact. So this is quite a long question. Find the equations and the point of contact of the tangents to the curve r equals a sine 2 theta. Okay, so r equals a sine 2 theta is a polar graph with 4 petals. Okay, so it looks like this. and I want to find the equations and the points of contact where it's parallel to the initial line and perpendicular to the initial line. Okay, so where points of contact where that happens. So we're first going to look at parallel to the initial line. Okay. Right, so let's begin. Parallel to the initial line is where dy by d theta equals 0. So I know that y is equal to r sine theta, and I know that r is equal to a sine 2 theta. So therefore y is going to equal a sine theta times sine 2 theta. Okay. Sine 2 theta is an identity. Is equal to 2 sine theta cos theta. And so when I sub that in, I get y equaling a cos theta sine squared theta. Right. I now want to find where dy by d theta is equal to 0. And I'm going to have to use the product rule, cos theta times sine squared theta. So this is going to become, well, I'm going to integrate the second function first. So sine squared theta becomes 2, and then I'm going to have my, 2 times a cos theta times sine theta times the derivative of sine theta, which is cos theta. And then I'm going to have the derivative of the first one, which is a times minus sine theta times the second one, which is sine squared theta. So therefore this is going to give me 2a cos squared theta sine theta minus a sine cubed theta equaling to 0. Okay, so I can divide by a, and that's going to give me 2 cos squared theta sine theta, cos squared theta sine theta minus sine cubed theta equals 0. And I'm going to factor out sine theta, so I'll get 2 cos squared theta minus sine squared theta equaling 0. This means that either sine theta equals 0 or this bracket equals 0, which means if I rearrange the bracket and move sine squared over, I'll get this. And then I'm going to divide by cos squared to turn this into tan squared. So therefore tan squared theta is equaling to 2. Now I know the solution for sine theta. I also just want to point out I'm actually only looking for the solutions between 0 and pi by 2, which takes out this answer. So I'm actually just looking for the solutions between 0 and pi by 2. So I know that sine theta will be 0 at 0 and at pi, but I can reject that. So the only answer I'm looking for this particular question is this. And if I solve tan squared theta, well, I know that tan theta is equal to plus minus root 2. And I'm going to focus on the positive only. So theta is equal to arctan of root 2, which is going to give me 0.955 to 3SF. Right. So remember, initially I'm trying to find the points of contact and the equations. Okay, so if I want to find the points of contact, I found theta, I now need to find r. And remember, r is a sine 2 theta. So for r equaling a sine 2 theta, if I sub in 0, then r is going to equal 0, which gives me the point 0, 0. But at that point, it's not. It actually intersects at that point. Maybe you can argue that it does if we just focus on the loop. We do have a point of contact. But it's similar to the previous case, actually intersects there because I go back down and come back again. So the only solution we are going to consider, we're not really considering that, is this one, r is equal to 2 sine of, well, I'm going to have to sub in the exact value. Because look, I have that tan theta is equal to root 2. Okay, tan theta, which I know is opposite over adjacent, which means this side must be root 3. And so therefore sine theta is equal to root 2 over root 3, and cos theta would be equal to 1 over root 3. So here I can say, well, r is equal to 2 sine theta, so therefore r equals 2 times root 2 over root 3. And so the point of contact, oh, I must do a, point of contact will be 2 root 2 a over root 3 and 0.955. Right. That's what we're working with. Now, we're only halfway through the first part. We now need to find the equation. Okay, we want to find the tangent parallel. So, and I can show you here again. If I sub in, let's say I have now 0, 0. So I want to find the equation of the tangent. I only have the point of contact so far. So for the point 0, 0, this is going to give me y equals 0, and I know therefore that r is equal 0. For the coordinates 2 root 2a over root 3, I just have to have a look here. I feel like I might have missed something. Yes, r is a sine 2 theta. Sine 2 theta. Not 2a sine theta. A sine 2 theta. So therefore r is a 2a sine theta cos theta. So I actually have 2 times a times root 2 over root 3 times by 1 over root 3, which gives me 2 root 2a all over 3, not this bit. Okay, so let's just continue with that. 2 root 2a over root 3, and my angle is 0.955. So I know that if r is equal to a sine 2 theta, I also know that y is equal to r sine theta. And I have r, right? R is that value. Therefore, y is equal to 2 root 2 over 3 a sine theta. Okay, and I also know that sine theta is root 2 over root 3. And so therefore y is equal to 2 root 2a over 3 times root 2 over root 3. And that gives me y is equal to 2, well, root 2 times root 2 is 2. So that's 4a over 3 root 3. That's my y. But as I said, I know that r is equal to, given that y is equal to r sine theta, I know now that 4a over 3 root 3 is equal to r sine theta, and therefore r is equal to 4a over 3 root 3 times cosec theta. Okay, that was a very long question. Question like this will probably be about 8-9 marks. Lots going on there, but we've made our way to the end. So I'd like to challenge you and suggest that you pause this video and see if you can use the same method to find the line that is perpendicular to the initial line. Pause it, have a go, and then press play and look at my solution. Okay, so I've written up the solution to part B, where we had to find the equation of the line perpendicular to this polar curve. And remember, it's between 0 and pi by 2. And so let's just talk through this. For perpendicular, I know that I want to find where dx d theta is equal to 0. So I start by finding an equation for x. I know that x is r cos theta. But I also know that r is equal to a sine 2 theta. So I sub in a sine 2 theta in r's place. I then simplify this and I get 2a sine theta cos squared theta. I then go and find dx d theta. I apply the product rule and I end up getting 2a cos theta times cos squared theta plus 2a sine theta times negative 2 cos theta times sine theta equals 0. When I simplify and factorize this, I divide by 2a as well. Simplify and factorize, and I end up with cos bracket cos squared theta minus 2 sine squared theta. Actually, I'm just dividing by a. I then solve this, cos theta equals 0, or this entire bracket equals 0, rearrange, and just like in the previous part A, I get theta equals pi by 2 in this instance, because I'm solving cos equals 0. But in the second case, same as before, I get tan squared theta equals a half, which becomes tan of plus minus 1 over root 2. But we're only using the positive because we're dealing with 0 to pi by 2. Okay, if I solve this end, I'm getting 0 and pi by 2. For tan of theta, it's exactly the same as before. I get that theta here is 0.615 radians. However, I can find an exact value for sine theta and cosine theta, which I can then sub in order to, here in r equals 2a sine theta cos theta, simplifies, and I get r equals 2 root 2a over 3, and that is the point of contact for where it is perpendicular. I then need to find the perpendicular tangent, and I do this for both 0 and pi by 2. I get r equals 0, but for the second coordinate, when I sub it in, I end up getting x is equal to 4a over 3 root 3. And I then sub it into r equals x sec theta, because I know that x equals r cos theta. So I rearrange that, and I end up with my final equation being 4a 3 root 3, 4a over 3 root 3 sec theta. So I hope that is useful. That concludes this, just the examples on this section. We will spend more time in class going over some exam questions on this topic. As always, if you have any questions, please do let me know.